So we start this class by doing a fair amount of review. I mean, we will be reviewing this first chapter as all this mostly pretty basic review of prior algebra concepts. You can see up here that our test is scheduled for the 22nd, so we're on the 4th right now. So we have about 4th, what does that make it, 18 days before we have our first test, and it'll all be over review stuff. I mean, you can see properties of real numbers. I mean, that's you'll see it is kind of basic stuff. But, you know, we're not trying to speed through this stuff. If there's some piece of this that you didn't get the first time through and that was hurting your ability to succeed later in the class, well, then maybe we can fill that hole. So these are the things we're going to do. Mostly this is just taken out of the book. They say that at the beginning, you know, this is what you're going to learn in this lesson. Won't always be exact, but it's pretty close. So by real numbers, right? You don't have to write anything you don't want. Again, you could just download this if you want to have this in your notes. This graphic itself is not taken from your book. They have something else that I thought was not as easy to see as this. This came from the Algebra 2 book. You know, the main thing, you know, we want to know what these numbers are, but there's a couple of main points. That if you wanted to write something, write the things that I write, not just this picture right here, which is a lot of copying. When we talk about real numbers, you always start with the set of counting numbers. With counting numbers are called natural numbers. 1, 2, 3, comma, dot, 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 goes on forever. If you add a 0 to that list, that's the whole numbers. So natural numbers and whole numbers. Right? You're not going to get quizzed on that. I will say the next two, when you take the SAT, they're going to use these words, and they expect you know what it means. They're not quizzing you on the word. It's just like part of the problem. If they ask you a question like, find an integer that meets these certain criteria, you can't be stuck on the word integer, right? Integer means all the whole numbers plus all the negative numbers. So it's not just 0, 1, 2, 3. It's also -1, -2, -3, forever. So you will get that word. I mean, I know it's an SAT question. They use the word integer. And they also use the word rational. And most of the time when we talk about rational numbers in any class, including calculus, the first day when you say, what do we mean by a rational number, you get a lot of blank stares. But we're really supposed to know what a rational number is. What is a rational number? Yeah. Any number? No. Yeah. Not what I'm looking for. Yeah. Fractions, right? When you say rational, think fractions. So rational numbers, 2/3, 5/4, those are fractions. That's an example of a rational number. Okay. Why then would they have 1 and 2 in that list? Go ahead. Well, anybody else? Why would 1 and 2, which are obviously natural numbers, whole numbers, integers, why would they be in the list of rational numbers? They are rational. Could you write them as a fraction? How could you do that? Julian? How about whatever is the number over 1? Isn't that the same thing? So any whole number or any integer, if you put it over 1, it's a fraction. So really, the rational numbers are any number you could write as a fraction. Even if it's not written as a fraction, it's still a rational number, right? As long as you could write it as a fraction. So stick it over 1, it's a rational number. That's why the rational numbers include all of these, right? It includes the natural numbers and the whole numbers and the integers. You take a decimal like 6.1. 6.1, we know is 6 1/10. Right? That's what the 1 means to the right of the decimal point. And you could simplify that. You could make that an improper fraction. That would be 61/10. So any decimal that terminates, that stops, you could write it as a fraction. In fact, this, I think, is a mistake in the graphic here, but it's probably what they mean to say here is that 2 is going to go on forever. And anytime you have a decimal that breaks into a pattern, that could also be written as a fraction. So rational numbers, right, equal fractions, includes decimals, that terminate, or if they don't terminate, if they repeat. Okay, that's rational numbers, right? That's like, let's just say that's like 1/2 of the real numbers. The other half there are real numbers that are not rational numbers, and they are called irrational. The beginning IR here is not rational numbers. And the prime example of an irrational number is a decimal that doesn't terminate and doesn't repeat. And pi is an example of that, right? What is the value of pi? 3.14156 goes on forever. Now, generally, if they're trying to get you to see what kind of number you're dealing with, and they want you to think irrational, either they're going to use pi or they're going to use some kind of a square root that can't be simplified. Like they can't tell you the square root of 9 because the square root of 9 can be simplified. That's 3. That's still rational, right? But the square root of 2 can't be simplified. So that will be a decimal that doesn't repeat and it doesn't terminate. So these are decimals don't terminate or repeat. Right? Those are the real numbers. Are those all numbers? The real numbers, are they all the numbers that there are out there? Do you have questions, Sam? Hand open? Okay. Are there any other sets of numbers you could think of? Because you're in functions, you actually did do this in Algebra 2. Do you remember what the other set was? I think I've got it in the next slide. No, I don't have it in there. Complex numbers, imaginary numbers. Remember the lowercase I? Yeah, there are numbers that are not real numbers. They would be imaginary numbers. And the biggest set of numbers is actually called complex. We'll get to that later. So let's say this first example 1 is just a classify. So each one of these numbers, let's just put it in the right category. How about negative pi? Just look, it's irrational. Put a negative in front of it, it's still irrational. So I'll call that here. How about negative 1/4? Okay, that would be it's a fraction, right? Rational. How about 6/3? Well, it's definitely rational. It could be simplified though too, right? 6/3 is 2. So if you look at the number 2, what other sets would you put it in? Right. Anytime you get a number like 2, I mean, it's natural, it's whole, it's an integer, it's rational. It's all 4 of those sets. Probably so we can call that integer, whole, and natural. How about 1/2 times the square root of 2? What do you think you would get? Let's say we know square root of 2 is already given as an irrational, but 1/2 is irrational. What kind of number do you think you'd make if you multiplied a rational times an irrational? Still irrational. Right? It'd still be irrational. But what if you multiplied an irrational times an irrational? What do you think you'd get? It's not, in every case, it won't be the same. Let's say I start with the square root of 2. If I multiply times the square root of 3, that's the square root of 6. Can that be simplified? Is 6 a perfect square? No. So that would be an irrational number. But what if I multiplied the square root of 2 times the square root of 2? What is that? The square root of 4, which is 2. So actually, in that case, irrational times an irrational is irrational. So it's not going to be the same in every case. What about negative 7.5? Rational. Negative 1. You know, probably the first set you'd probably put it in as integer, right? It's not a whole number. It's not a natural number. It could be rational. It could be integer. How about 8? Natural, whole, integer, rational, all 4, just like this. Rat, int, whole, and natural. And then we get to negative 22 again as like the negative 1. It's an integer, and it's a rational number. Okay. Yeah, and Logan. Because the integers are only the whole numbers, including the negative numbers. So it doesn't include anything in between the 0 and the 1 or the 2 and the 3 and all that. It's no decimals, no numbers that have to be written as decimals or fractions. Yeah, it turns air conditioned down. Okay, good. Right, the real number line, which we plot things on a number line, has all the real numbers on it. You know, there's 0, if I put the 0 on it and label that as the middle, then to the right of 0, it's positive, and the numbers increase 1, 2, 3, 4, and they keep going on forever. Right? To the left of 0 is negative 1, negative 2, negative 3, negative 4. So the numbers are getting bigger, but because they got negative signs in front, they're actually getting smaller to the left, and they go on forever in a negative direction. Real numbers are, this number line is continuous. When you see a real number line, you don't just think of it as just the numbers that are labeled. There's actually a number for every point on that line. There's infinitely many points. In fact, there's infinitely many points. Even if I just zoom in on like 0 to 1, there's infinitely many points in there. And if I zoom in on just like one little piece in there, there's still infinitely many points. You can never get to a place where there's a gap. There's always going to be a number in between. So it's continuous, it's infinite. And how do we write the number infinity? Yeah, it's like an 8 laying on its side, right? So we would, over here, this is going towards positive infinity. So that's the symbol for infinity. Over here, it's going towards negative infinity, right? Negative. Good. We're good? Do you have a question, Z? Did you have a question? Z, do you have a question? Okay. We good, Damien? Okay. So now, if we want to plot numbers on the number line, you got to figure out where they go. I mean, it's easy if it's 1, 2, 3, 4. You know exactly where it goes. How do you tell where 5/2 goes? Julian. Make it a decimal, right? What is the decimal value of 5 halves? You know, this is 2.5. Okay, where would I mark 2.5 on the number line? Right, so it's more than 2, less than 3. So more than 2, less than 3. It's actually exactly halfway in between. So 2.5 would be, or 5 halves would be about right there. Okay, negative 1.6. What two numbers am I going to mark that in between? Okay. What two numbers is negative 1.6 in between? Negative 2 and negative 1, right? So it's somewhere in the middle of here. Should I mark it exactly halfway in the middle? Should it be closer to negative 2 or negative 1? Right, negative 1.6 is a little more than halfway to negative 2. So I wouldn't go right in the middle. I'd make it just a little bit to the left of that, negative 1.6. Okay, how about negative 3/4? What's the decimal value? Say again? Well, what's a decimal value of 3/4? 0.75, right? So that's negative 0.75. Okay, what two numbers is that going to be in between? 0 and negative 1, right? And so would it be closer to the 0 or closer to the negative 1? Right, it's closer to the negative 1, right? So, I mean, if you're counting in fourths, right, it'd be negative 0.25, negative 0.5, negative 0.75, so about right there. Okay, and then where am I going to put a 0.7? In between which two numbers? Connor? Right, between which two integers am I going to put 0.7? 0 and 1, right? 0.7 is less than 1. It's 7/10. So you have to go in between 0 and 1, closer to the 0, closer to the 1. Closer to the 1. So about, maybe I'll estimate it. These are all estimates anyways. So if you have to graph things on the number line, turn it into a decimal. Figure out where it goes. Now, the one thing you know about a number line, because it's, you know, going towards negative infinity on that side, positive infinity on that side, any number which is to the right of another number on the number line is bigger. Right? By definition, if it's to the right, it's bigger. If it's to the left of another number, it's less. If everything is in order. Okay. Easy stuff, right? So if we want to make an order to this and represent the order of the numbers, then we've got these 4 inequality symbols, which you probably know, but there might be some out there that still, maybe you're doing this alligator thing, trying to figure out, you know, does that mean that one eats the other one or something? Right. The greater than or equal to, what makes this the or equal to? The bar underneath, right? Less than, or equal to. So like, if I'm saying greater than, is 5 greater than 5? No. Is 5 greater than or equal to 5? Yes. So the or equal to picks up that point. Good, Emily? You good? Anybody? Okay, so let's pick the right one of those symbols to put in between those pairs of numbers. What symbol or symbols would I put in between the 1 and the negative 5? Say again, Ariel? Greater than? So, greater than, right? Could you say greater than or equal to? Sure. Greater than or equal to. How about 3 halves and 7? How do you compare the value of the fraction to the whole number? Yeah, maybe think of it like a decimal, right? This is 1.5. Okay, now compare. 1.5 and 7, what symbol goes in between? Less than. Negative 2/3 and negative 3/4. We're going to have to turn those into decimals. Probably not everybody's going to have a good handle on what the values are. If you put that in the calculator, negative 2/3, it is negative 0.6 repeating. Right? Negative 3/4, we just did that on the last slide. That was negative 0.75. So what symbol goes in between those two? Is negative 0.6 bigger or less than? So again, if you think of it on the number line, they're both in between 0 and negative 1. Right? This negative 0.6, let's say, would be about right here. Negative 0.6 repeating. And negative 0.75 would be even further towards the negative 1. So which is bigger? How do you know which is bigger? The one that is to the right, which makes it that one. How about the negative 3.5 and 1? What's the symbol? It's a less than. That's an easy one. And again, all those there, if you put it or equal to, it's still right. Okay. Good. Okay. Graph. Now, if we want to graph an inequality, then there's two things that go on the graph. One is you got to decide what to do at the point. Yeah. So at negative 3, I got to put a circle. The only question is, should I make an open circle or a closed circle? What kind of circle do you use if it's a greater than? Open because it doesn't say or equal to, right? So if I go to negative 3, I put an open circle. And then I've got to do the shading, one side or the other. Right? We want to shade the part of the number line that has all the values of x that would make that true. Should we shade to the right or to the left? I mean, greater than on the number line means to the right. Right? So we would shade this way. Again, so what does it mean, the open circle? It means that that negative 3 would not solve this. Negative 3 is not greater than negative 3. Okay. This kind of inequality is called a 3-part inequality. And what it means is we want the values of x that are in between 0 and 4. So if you see on the number line 0 and 4, we want to shade everything in between. Right? So that's going to be here. Now, what kind of a circle will I use on 0? Right, that is open, because it's not or equal to. What kind of a circle will I use on 4? Closed. Right? Because is 4 greater than or equal to 4? Or 4 less than or equal to 4? Yes, that would satisfy it. So then we want to shade everything in between. So you got to think of these 3-part inequalities as x is in between 0 and 4. I mean, sometimes when students see this kind of thing, they want to treat it like it's 2 different inequalities, right? X is greater than 0, x is less than or equal to 4. In a way, it is, but then you would have to connect those two inequalities with the word and it would mean only where those overlap. It's much easier, just think of it like an in-between, right? Whatever's the x values are in between that number and that number. And then the only thing you have to decide is open circle, close circle. Okay. Now, here's another three-part inequality. Again, it means that the x is in between -2 on the left and 3 on the right. But what this slide is about is the book uses an interval notation where they're using brackets, round brackets and square brackets. And the way you would write what this says with the brackets would be like this. You would use a square bracket on the left, -2, comma, 3, round bracket. So the or equal to is represented with a square bracket. That means it's or equal to. The not or equal to is a round bracket. It means does not include that point. So you have to be familiar with this because they're going to see it in the book. It'll be in the homework problems. It'll be in the book. It's just kind of like the way they like to do this. It means the same thing as this. There's no difference. These two are the same. What's that? Just another way to write it. It's just a notation, right? So how would I write this one if that's the example? Okay, so round, then what? 0, comma, 4, square bracket, right? Okay, now if we do these, x is less than or equal to 2, right? How would I write that? Okay, so we don't have a part on the left like we did with these three-part inequalities. It was kind of easier to see what goes on each side. Right? If x is less than or equal to 2, that would be on the graph. It would look like this, right? In terms of the interval notation, definitely the 2 is on the right, so you would have a bracket 2. The question is, what is going to be the endpoint on the left, since that arrow goes forever? Negative infinity, right? So if you have an interval that doesn't stop, then you have to use an infinity symbol to say that's the end of that interval. It means it goes on forever to the left, right? How about this x greater than -3? How would I write that with the interval notation? Julian? Okay, if I graph it, I would graph open or close circle. This one here, open or close? Open, and shade to which side? To the right, because it's greater than. That means greater than on the number line means to the right. Okay, now, how does that look with the interval notation? What would be the left side of that interval? It's a -3. Is it round parentheses or a square bracket? Round parentheses because it's not or equal to. So -3. Right. What is on the right of that interval? Since the arrow goes forever to the right, positive infinity. Right. So but this means the same thing as this. You want to go? Okay. This means the same thing as that. You're probably pretty comfortable looking at x less than or equal to 2, but maybe not so much with this. But again, you're going to see it, so don't be surprised by it. If you're answering like a test question for me, I don't care how you write it. I don't care at all. There's never going to be a time that I'm quizzing you on that. If you want to use that, just use that. But you don't want to not understand what they mean when they say that. Okay. Absolute value. Right? We know absolute value is these straight brackets, let's say. And what does the absolute value do? I mean, I'm using all, variables here. The absolute value of A, if A is greater than or equal to 0, what does the absolute value do to it? For example, let's substitute a value that's greater than or equal to 0. How about 2? What's the absolute value of 2? 2, right? It does not change the value, right? If that's a positive number, then the answer is the same number, right? But what if that number is a negative number? What if A is less than 0? What if that was a negative 2? What would that do? It would flip the sign, right? If A is negative 2, then what is negative A? Positive 2. So it means the opposite of what you're starting with. So when you have a negative, if you take the absolute value, it flips the sign. That's all this is saying here. Flip the sign. If it's negative, leave it alone if it's not. So, for example, what is the absolute value of negative 15? 15. Okay, what is negative absolute value of negative 6? How many say negative 6? Okay, if you left off the negative, which is not inside the absolute value, then you would say that is 6. And then you would stick the negative in front. Right? Don't try to cancel them out or anything like that. They don't cancel. Good? Okay, evaluate the absolute value of x over x for x greater than 0. What would it equal? And if you're confused when you look at it like that, substitute a number. Give me a number greater than 0. 4, okay? So what is the absolute value of 4 over 4? The absolute value of 4 is 4. 4 over 4 is 1. Okay. Now see what happens when x is less than 0. Give me a number that's less than 0. Negative 4, right? Absolute value of negative 4 over negative 4. Right? What's the absolute value of negative 4? Positive 4. What is 4 over negative 4? Negative 1. So the absolute value of any number divided by itself, if the number is positive, it'll be 1, because there won't be any difference. You know, the absolute value is going to be the same thing anyways. But if the number is negative, that's actually going to be a negative 1. And that does come up in something that we do later on. Actually, we'll see. Yep. You in here? Okay. Have a seat. All right. Now, just talking about number line, right? We're not talking about in 2 dimensions in the coordinate plane. If you want to know the distance between, these are open, there's one there. The distance between 2 points on a number line, it's the absolute value of their difference. So just subtract one from the other, make sure it's a positive number. You know, the bottom line is that distance is always positive. So if you subtract and generate a negative number, make it a positive number. Distance is always positive. So again, how would we find the distance between 35 and negative 23? Right, the distance is 35 minus negative 23. What is 35 minus negative 23? Yeah, the minus a negative makes it a plus, right? Which means 58. Now, what if you subtracted in the reverse order? So you had negative 23 minus 35. then you would have got a negative 58. Right? But because this is distance, and you know that distance has to be positive, you take the absolute value, and that's 58. So distance is always positive. If you happen to subtract in the reverse order and you make a negative number, just flip the sign. Yeah, it's kind of a formula. So they're using I've never seen this before, right? Where they use D parentheses and the two endpoints to mean distance, but it's pretty obvious what they mean by it. D must represent distance. You good? Damien? Good? Okay. And Logan, you okay? You okay? Okay. Now we got to talk about this. Some of it's just vocabulary, right? Because we're going to talk about polynomials that have with certain terms that we use, and you have or vocabulary words that we use. This example right here, x squared minus 5x plus 8. Right? That is an algebraic expression. It's actually a quadratic. How many terms does it have? 3. Okay. Terms are separated by pluses and minuses for addition and subtraction. So when you see this minus and that plus, it's got to be in between terms. That means there's 1, 2, 3 terms. Right? Terms are separated by pluses and minuses. For example, you wouldn't say 5x is 2 terms because there's not a plus or a minus in between them. Right? It's only when there's a plus or a minus that separates terms. So this one has 3 terms. If there's a number in front of a variable, that is called a coefficient. Okay, and we will use the word, just assuming we all know what we mean by coefficient. So definitely, the coefficient here is negative 5. It includes the minus. What's the coefficient of the x squared term? Yeah, if you don't see a coefficient, it's 1. Right? So there's a 1 right there as a coefficient. And then when you have a term like this last term, 8, and it doesn't have a variable, that's called a constant term because it doesn't change, right? No matter what you plug in for x, the 8 is always the same. That's a constant. So when it comes to expressions, we do 2 things with them. We evaluate and we simplify. Right? We evaluate by plugging in values for the variable to see what it equals. And we simplify by combining like terms, right? Both things I know you've done before. Wait, is a parade in here today? Okay. Okay. You good? Katerina, you good? Okay. So here's some examples. Evaluate negative 3x plus 5 if x equals 3. What are you expected to do with the 3? Put it in for x, right? It just means take this and put it in the place there. So that would be negative 3 times 3 plus 5. Which is negative 9 plus 5, negative 4. Okay, how about this one? Try this one on your own. See what you got. 3x squared plus 2x minus 1 if x equals negative 1. Who's got an answer? Who's got an answer? Sean? What's the value of this one?
0.
Got a 0. Who else? Anybody else get a different answer? You got 3 minus 2 minus 1, which is, you got it. You're right there. Julian, what did you say? It's 0. Did anybody get anything other than 0? It is 0. Right? This is the kind of place where we tend to make mistakes. Because the variable is negative, because there's a squared going on, we make a lot of mistakes with this one particular kind of problem. But it doesn't sound like anybody did, or at least they didn't say it. All right. So you got to, when you plug in, you got to plug in the negative 1 squared plus 2 times negative 1 minus 1. Okay, the negative 1 squared is positive 1. And again, since we don't have the calculators, a lot of you would have made the mistake of putting in your calculator without parentheses and would have had the error. But maybe because you didn't have it, you didn't make the mistake. All right, so this is 3 times 1 minus 2 minus 1, which is 0. And then the last one, let me just substitute 2 times negative 3 divided by negative 3 plus 1. What does that equal? 3. Negative 6 over negative 2, which is 3. You're right. So evaluate a function means substitute for the variable. You good? Attention? Okay. Okay, so these are the properties of real numbers. Again, I took this graphic from the Algebra 2 book. In our book, they call them the rules of algebra, but they're the same thing. Honestly, I've never heard them called the rules of algebra. I've always heard them called properties of algebra. But most of these you've seen before, like A plus B equals B plus A. 2 plus 3 equals 3 plus 2, right? They're both 5. Order doesn't matter. That's called commutative. If you move the parentheses, you're adding A plus B plus C. It doesn't matter if you add A plus B first or B plus C first. Same thing. That's associative. What number can you add to another number and get the same thing back again? 0, right? 0 plus anything is the same thing. That's called the identity for addition, right? 0 is the identity element. What number do you multiply that doesn't change the value? 1. That's the multiplicative identity, right? The inverse is, what number do you add to get 0? You add the opposite. 3 plus negative 3. Negative 5 plus 5, right? You just add the opposite, you get back to 0. Or if you multiply, this one, A times 1 over A, what they're trying to say, like if I multiplied 4 times 1 over 4, that equals 1. The 4's cancel, and it's 1. But it's more than that, right? It would also be something like, what if I have 4 sevenths? What would I multiply times 4 sevenths to get 1? 7 over 4. You just flip it. So it's not just like this 1 over situation. What it means is flip the fraction, right? And if you start with a, then a over 1, and when you flip it, is 1 over a. So 7 over 4, because these all cancel. Right? And distributive property is right there. And I wouldn't worry about this closure property, which I've really never seen anybody use that. But no, in higher math kind of classes, you do use that. But at our level, we probably wouldn't. All it really means is that if you add 2 real numbers, you get a real number. You don't end up outside of the set of real numbers. So which property does this look like? X plus 9 equals 9 plus x. Commutative for addition. So that would be this one. Right. Which property does that look like? Is that distributive? Do you have a plus in there? It's a, somebody just said it. It's associative, right? What changed from the left side to the right side? The grouping, right? The parentheses. They were here, and now they're here. So that would be associative for multiplication. Okay, now you have distributive. Now, most of the time we look at distributive, it shows the multiplication on the left. This one does not. It shows it on the right, but it still works the same way. Right? This y squared gets multiplied times 2, and the y squared gets multiplied by 5x squared. Distributive. So the properties of equality are basically saying if you have an equation, you can add, subtract, multiply, divide, do whatever operation you want if you do it to both sides. You can and you must, right? That's how we solve equations. That's how we isolate variables. Just keep doing the same thing to both sides until you've isolated a variable. And those could be called the properties of equality. Okay, then the last little bit of review here, fractions. Right? When you are solving, this is called a proportion. What's the method we use to solve? So if I said 1/2 equals x over 8, how do I solve? Cross multiply, right? It's to solve an equation, you go like this. AD equals BC. That's what this says right here. In this problem, it would be 2x equals 8, x equals 4. When you have fractions, most of the time, if you look carefully in the book, a negative sign in front of a fraction will not be written in the numerator or the denominator. It's exactly in front of the fraction bar. Yeah. Yeah. Okay, thank you. Okay. Okay. If you see a negative in front of the fraction, I mean, you could assign that to the numerator. You could assign it to the denominator. It doesn't matter. But you just can't assign it to both, right? The negative in front does not mean negative a over negative b. Negative a over negative b, the negatives cancel. That's positive a over positive b. Right? So just saying, if you got a negative in front of a fraction, you could put it on top. You could put it on the bottom. Just don't put it on both. This one is trying to, it actually would make more sense going in that direction. What if I have 6 over 8? How do I simplify that? Divide both by 2. They have a common factor of 2. So if I write it like 2 times 3 over 2 times 4, that's what this is saying right there. They have a common factor. And what can you do with that common factor? They cancel. That's all this is trying to say. You can get an equivalent fraction by multiplying by the same number. You can simplify a fraction by canceling common factors. Right. The next one is saying, how do you add or subtract fractions when they have the same denominator? Right. If I say, what is 1/8 plus 2/8? How do you add them up? How many? And Logan? Add the tops, right? Don't change the denominators. As long as they're the same denominator, just add the numerators. So that would be 3/8. Okay, how do you add fractions when they don't have the same denominator? You got to have a common denominator, right? And this, what they're saying here, which is not exactly the way we teach it, is just, okay, well then multiply the first, if the common denominator is going to be the product b times d, then you would have to multiply this first fraction times d over d, the second one times b over b, and now they have the same denominator, so just add across in the numerators. Now, the only thing wrong with that, what they said, is that's not usually what we do. We usually just don't find a common denominator. What do we find? We usually got a word in front of common denominator. Least common denominator, right? Would this find the least common denominator? Not necessarily. What if I was trying to add 1/4 plus 1/6? If I was going to do what they're saying here, I would say my common denominator is 4 times 6, 24. And then I would multiply this one by 6 over 6, and this one by 4 over 4. But is that really the common denominator, the least common denominator? What's the smallest number that both 4 and 6 divide evenly into? 12, right? So we actually have a process when we do rational expressions that would find the least common denominator. This wouldn't necessarily do it. You would end up getting something like, this is 6 plus 4, 10 24ths, and now that has to be simplified, which is not a problem, right? We could do that. 10 over 24 is 5 over 12. Okay, how do you multiply fractions? A over B times C over D, what's the process? What's that? Straight across, right? Multiply the numerators, multiply the denominators, right? Don't confuse that with that. It's not a cross multiply. Cross multiply is when you've got an equals in between, then you can do the cross multiply. When you're multiplying fractions, you just go straight across. That is A times C over B times C. Just go straight across. How is it that we divide by a fraction? Dividing by a fraction is the same as multiplying by the reciprocal. So don't change the first fraction, you change the second fraction and multiply. And again, now that it's a multiply, how do I do that multiplication? Straight across. A lot of times, you guys didn't do this at all, but a lot of times when I ask how to do the multiply fractions, I get cross multiply. And nobody bid on that. Okay, let's do this. Example 14. 7 over x divided by 3/2. What should be my next step? 7 over x times 2/3, which is 14 over 3x. Okay, multiply fractions. 3 over 5 times x over 6. Straight across, right? Straight across. 3x over 30. All right, could we simplify that? No. Is there a common factor between 3 and 30? 3, right? So if you divide out the common factor of 3, you would have x over 10. Okay, here's the adding fractions that don't have the same denominator. Again, if we follow their little formula there, then we're going to make a common denominator of 5 times 10, which is 50. Now, is that the least common denominator? No. The least common denominator would be 10, right? So you'd have much smaller numbers to deal with. Now, in order for this fraction to have a denominator of 50, you have to multiply times 5 over 5. In order for this fraction to have a denominator of 50, you multiply by 10 over 10. Now they both have a denominator of 50. Add the numerators. 5x plus 20x. Which is 25x over 50. And how would that simplify? What's the common factor? 25, right? If you cancel the 25s, you're going to get x over 2. So if you would have found the least common denominator, you would not have had that simplification to do at the end. It would have been already the 1/2. And that's it. So the homework is, just a mix of those kinds of problems. Again, this video of what we just did will be on the website. If you have any issues with anything we've done, it's taken pretty much from the book. But if you want to look at the video, if that helps you through it,